Hello, everybody. I'm very pleased to welcome Dr. Brittany Duncan here for Robotics Seminar. Brittany is an assistant professor at University of Nebraska, Lincoln, and she is also the co-director of the Nimbus Lab there. Before joining University of Nebraska, she did her PhD from Texas A&M with Professor Robin Murphy on search and rescue robots. And before that, she did a VS from Georgia Tech. Her research interests are mostly lie in the intersection of human factors, behavior-based robotics, as well as unmanned systems. And she likes to focus on how humans can naturally interact with robots, whether it's individual interaction or as a part of ad hoc teams. So today she's going to present on drones in public spaces. So let's welcome her again.
Thanks, and I'm glad you guys can make it. So the only time I call them drones is in this title slide. So sorry, for the rest of the talk, there'll be small unmanned aerial systems or small unmanned aerial vehicles. But, you know, that's a lot of words to put in a title. So I just go drones in public. But we will be kind of focusing today on distancing and communication with general users. But I'll start out much broader than that. So like Tapo said, I'm Brittany Duncan. I'm an assistant professor. I'm also the co-director of the Nebraska Intelligent Mobile Unmanned Systems, or Nimbus Lab, at the University of Nebraska. So my overall vision for the world is to improve human-robot interaction for real users in real-world situations. And I know most people who work with human-robot interaction believe that they also want to help real users in the real world. But I think that it's important to actually get with people who have complex domains that they're working in, and see how our assumptions break down and how quickly they do. So we'll talk more about that as we talk about the different domains that we have current projects in. So Tapo did say I worked with urban search and rescue responders as part of my dissertation work. I also work with people in the prescribed burn community now as a professor. And these are specially trained users with complex use cases. So they have very, very big needs for robots and really great ways in which robots can fail them. But I also look at how people in the general public can interact with robots in everyday interaction. So people who may not have intended when they left their house today to interact with a robot, but now they are, and how does that work? And so that's kind of what we're going to be focused on more today during this talk, once we get past my overarching research vision. So this breaks down into kind of adapting autonomy into more effective user control, which I'm going to talk about briefly before we get into the novice interactions with small unmanned aerial vehicles, which is the distancing and communication work. So for the adapting autonomy for more effective user control, this encompasses interface design, user responses to failures, and understanding users and how to adapt to them. So for interface design, I'll talk more about the prescribed interface, prescribed fire interface later, and why we have drones dropping fireballs. There's a really cool video that goes along with it, but this kind of teases that, and this is actually just one interface we designed for specially trained users in complex domains. And so this is for prescribed fire igniters. If they wanted to take one of our drones out to the field, they could use this interface to actually tell it how they want it to drop fireballs. So how far apart they want lines spaced and different things. And they can see the drone on the map, and they can see the fire front. So these images are from video. So this is a FLIR video that shows exactly where the fire is at any given time. And this is a visual camera that shows kind of where the fire is at any given time, but it gives you context for where the boundaries are. So you can actually see the road out here that you can't see in this one, but you can see in that one. And so eventually we could use all of these together to figure out where the fire is and go ahead and propagate that to the map. Right now what you'll see is these points where they can actually drag the fire line if it's in a different place than they thought it was. This does a couple things. It lets the drone avoid places that are on fire, which is great because we don't want the drone to be on fire. It also will save its energy to ignite places that are not on fire and adapt its plans based on what it knows about the world. I also created a sketch interface for urban search and rescue responders on the very first iPad, so that gives you some context for how long ago it was. But we were curious how multi-touch gestures could actually be used by real-world responders, and we found really, really interesting things by working with real people. One of those things we found is that most firefighters have calluses on their fingers. Calloused fingers don't conduct electricity well. So what they do is they use their knuckles for multi-touch devices. Well, when you're doing knuckles, you can't really drag things far apart because your fingers don't work in that way. So this is one of those things where I say, anyone who I've met with today who says that they're getting out of the lab and talking to real people in the environment that they're going to use something makes my heart happy, because that's when you find out all of the things that you don't know about the world, is when you talk to people who interact in those spaces. So another piece that I work on, sorry, this will be kind of fire hose at the front, where I just tell you about all these cool projects, and then you can ask me about them later. But these are things that I'm not really going to talk about in the talk today. So user response to autonomy failures. I don't have to tell all of you that autonomy is becoming more ubiquitous. You're helping to make that true. But autonomous cars, small unmanned aerial vehicles, and also aviation. It's creating opportunities for systems to fail in both expected and unexpected ways. So in expected ways, you can give the user a heads up and say, hey, something bad is going to happen. I may not know what, but something bad is coming. But in unexpected failures, you just say, hey, I'm out, it's your turn. And so that's not a great handover. And if we don't know how people are going to respond, then we can't respond well, right? We can't help them respond. So one of the things I'm investigating is, basically, this has been done in autonomous cars and aviation, but nobody's really looked at it for small unmanned aerial systems, is when the system's failing, how long does it take for people to respond and to identify these failures? So one of the things we found was actually that as we made the deadlines for responding longer, it wasn't actually a linear relationship between the response time that's allowed to the failure and how long it took people to respond. But people got far more accurate the more time you gave them. So if you gave them 1 second to respond, that's what the red bar is, then it took them 1 second to respond, and they were pretty noisy in their responses. They missed about 10% of failures. If you gave them 5 seconds to respond, it took them about 1.5 seconds, and they only missed 2% of failures. And if you gave them 8 seconds to respond, it only took them about 2 seconds to respond, and they got 100% of failures. They could recognize them in time, and they could recognize them well. So this is really cool work that, like I said, I wanted to tease, but I'm not actually going to talk about it all. But I'm really excited about it. So if you want to talk about it, let's do it. Then the final piece of the user portfolio that I'm not going to talk about today, except for a minute to tell you about it, is user understanding and adaptation. So understanding the impact of a single person, an individual user, on performance in shared autonomy situations, and trying to understand if there are specific things about people that we could generalize to and adapt to. So by understanding individual interactions, can we better understand how to interact with lots of people? And so the specific question we focused on here was locus of control. So your locus of control is either internal or external. So either you believe that you control your destiny and all the decisions you make drive you to where you're going, or you believe that the world kind of happens and you're just along for the ride. And most people don't fall on these two extremes. They fall somewhere in the middle. But this is a intrinsic user quality that you have that changes how you interact in the world. And it's been hypothesized for a while that if you have an internal locus of control and you're presented with autonomy, you will not interact well with it because you will fight it for control. You want to be in control, and it is trying to supersede your control, and you don't like that. So whether this is in the form of you're taking me the wrong way home because this is not the way that I would go, and so you fight with it, or other ways that it can show up. But it actually turned out that locus of control didn't have a huge impact. So we tested it using a telepresence robot in a maze, so the maze is down there, and we had either linear obstacle avoidance, where it would keep you very far from the obstacles, it would keep you kind of in the center, or we had exponential obstacle avoidance, where you could go up and basically touch the obstacles, but you couldn't forcefully run into them. And it turned out that locus of control did not appear to have a big impact on user preference or system performance in any of the ways that we could cut the numbers. So locus of control was not the one we were looking for, but that does not mean that there are not intrinsic user qualities that do have these impacts, and we just think it's probably overridden by something else. So that's the quick and dirty on the other things that I do. Now we'll talk about novice interactions with small unmanned aerial vehicles. And this is split into distancing and communication. So here's a figure that I really love. It's an orienting overview of this work, and it was part of my career proposal to explain the different things I'm going to be doing. So this part A depicts a drone is taking a family in a nursing home and it's taking them to somebody's room, but it needs to land immediately. So what it does is it spirals down, and this indicates both that it is landing and where it is going to land. So it's a small gesture because it's in a small hallway. Now on the other side, there's B, and you can see the family starts out in this foyer, and the drone is closer to them, and then they go into a smaller hallway, and the drone gets further away, because as you transition between spaces, your personal space requirements change, and so it should be further away to respect your space. Then finally, in C, there is a drone that's indicating that people need to clear this area to let the responders out, and this is a much larger gesture than it was in the hallway when this drone was spiraling down. A, because there is more space, but B, because it needs to be more visible for other people to see it. And so this is actually scaling the gestures to the size of the environment that people are interacting in. So this is a really cool figure to me because it conveys in little stories what the drones could be doing and how they could be interacting with people, why they need to do these different things. But it's also just kind of fun. So drones are becoming more ubiquitous. They're going to be in different applications. And that's one of the motivating things of this talk. So, all right. Now we're going to get to the meat and potatoes of the actual talk, now that I've fire hosed you with all the things that I love. And we'll just talk about the distancing and communication and some of the applications from here on out. So I'll motivate it and tell you why this is an important problem or why I think it's important. Then I'll give you some applications. So some of the actual field-based work that Nimbus is doing that kind of contextualizes where this is going. Then we'll talk about the distancing work and transition into the communication work. And finally, we'll talk about the future work. So all of this, what I want you to get at the end of the talk is that distancing and communicative flight paths are important fundamentals in human small unmanned aerial system interactions. That they are the building blocks for the rest of the things that we want to do if we want to interact with novices and the general public. Very cool. All right. So why is this important? It's important because Amazon wants to bring packages and drop them in your front yard where kids play, dogs play, neighbors walk through, things like that. There's all kinds of really fun problems with that. But one of the big ones is, as it's coming in to land, how will it communicate that to you so that it can land safely? Because all you want is your sneakers that are underneath it, and it needs to be safely on the ground for you to get those sneakers. The other picture is from the Wild West days of drones. So this is an octocopter that was out of Running the Bulls. It was there to get pictures, and it looks super safe, right? You want to hang out underneath this guy. But this was a Running the Bulls in Virginia, and so people went and bulls chased them. Less people were hurt by the bulls that day than by this drone when it crashed into the crowd and injured 5 people. The bulls injured 2. So that's not great, and we want to be able to communicate with people better and maybe not crash on their heads. We can do that by not flying over their heads, but we can also do it, hopefully, by just being better. So that's kind of my motivating scenario here. Also, Amazon's not the only one who wants to deliver stuff. What is it? Google's has delivered burritos. I think it was one of the more established tech companies just filed a patent to identify people who look tired in crowds and deliver cups of coffee to them, which sounds terrifying for lots and lots of reasons. But everybody's coming up with cool things that drones could deliver to you. Hot coffee may not be one of them. Hopefully it's iced coffee. But everybody wants to deliver things to you from drones, and so these interactions are going to get closer to us, and they're going to need to be more communicative as they are. So the next video I show you is potato quality. I'm going to go ahead and warn you now. It was recorded on actual videotapes and then put onto a computer. So it is not what we expect these days, but it's still a cool video, so I'm going to show it anyway. All right, so this is from 2009, where we interacted with A Midsummer Night's Dream with these actors. We flew over their heads. We had these little fist-sized helicopters. You can see that one crashed, and that fairy looks really mad. We had middle schoolers flying these, which was lots of fun for everyone. But what that really meant is they crashed a whole lot. So this is a different version of it. So you can see her pick it up and gently relaunch it. And then it goes up and it immediately crashes again, because that's what happens when middle schoolers fly your drones. And so you'll see it go up, and then you'll see it like beeline out to the crowd here in a second. So it's already done that. So now the fairies are mad. They're going to go back and get their drone, which is great. They went along with it. We really appreciate their help on this one. So they rolled with all of it, and it was great. But what we found here was kind of an early intuition on how people are going to interact with drones in public. And that is, people don't really understand that. We think they do, but they don't. And so if the drone was flying overhead and something unexpected happened, it stopped going forward when it should be going forward. People would look up at it and they would like flick it, thinking that they were helping it, right? They're helping it go forward, but it would fall out of the air because it's not very stable. They also, if it crashed in the audience, they would pick it up and they would look at it, and we all know that helicopters don't fly if their blades aren't spinning, right? That's pretty fundamental. Most people know that. But they would look at it and they would go, it came from the air and it belongs in the air, and they would toss it into the air. And so, of course, middle schoolers, some of them would try to recover it in midair. They're never going to do that. So it would crash back on the person again, which is not great. And if the middle schoolers started up the props, then it would actually be spinning as it crashed into them again, which was super fun for everyone. But, so with almost 100% certainty, they would do the wrong thing if it crashed into them before it crashed on stage. But if it crashed on stage and the fairies picked it up and gently held it in the air until it relaunched itself, with like 90% certainty, people would do that. They would follow what they had just seen. And this goes back to fundamental psychology principle, which is called social proof, which is in the world, if you are interacting and you don't know what to do, you look around and you see what everyone else is doing, and you just do that. That's how we evolved as a species to interact in the world. And it turns out it's pretty effective. And so that worked well in this scenario, and it was really neat to see that actually show up where they had a visible way to interact correctly, and they would follow that. Another interesting thing we learned about this in this interaction was that we had these small helicopters that won't hurt anybody. They're the little ones you buy at the mall. They're like $30. They're fist size, and you can stick your fingers in the props and they won't hurt you. And that's great. And so we showed that to the actors. And we said, okay, so if this thing falls on your head, look, you can stop the blades. It's not going to hurt you. If it doesn't, hit you right in the eyeball or something, you'll be fine. They didn't all start wearing glasses the next day, so we were okay. But then we brought in our larger aircraft. It was a meter across, military quadcopter, and they kind of thought it was the same, right? So it was all carbon fiber. It was very hardened. It was an $80,000 system, and it was only coming in for like 2 parts at the very beginning and the very end. It was Oberon's baby fairy, for those of you who are into A Midsummer Night's Dream. And so it would come in, and they would dance underneath it, and they were all like touching it and like not scared of it at all. They were treating it like an AR drone, basically. And this was before the AR drone actually came out, by the way. And so then we had to stop and go, oh, no, sorry. That is the flying weed whacker of death. Don't get near it, because the carbon fiber blades will chop your fingers off. These are toys. You can play with them. And so it turns out another thing that we didn't really think through or know until we got there was that people have this assumption of product safety. So in the world, when you interact, our government does a pretty decent job of making sure that you're not just going to walk down the street and die. And so people are kind of used to this, right? If I am interacting with something in the world, it's probably safe enough that it's not going to kill me. Except in rare cases, somebody else backs into you or backs over you with a car. Well, it's a person at the controls. It's not something that you just kind of encountered. Most things you encounter in the world are pretty safe. So this was kind of early things we figured out by taking robots out and seeing what human beings do when confronted with robots. And I love this picture. So there were cameras that took good pictures. There just weren't video cameras that took good videos at the time. So now I'm going to motivate it a little bit more with some other examples from Nimbus, things that we're doing now. I told you we have fireball dropping drones. We're going to see a video of that in a second. But I really love the picture of us with the fire behind us. We made fire. Computer scientists make fire probably more often than we should. But this time we meant to, and we got to stand in front of it, and it was awesome. There's a water sampling robot there. There's a crop height measuring robot over there that I'm not really going to talk about. but I like that picture. So in the Nimbus lab, we focus on close interaction with the world and the practitioners who would actually deploy these systems. So we primarily work with unmanned aerial vehicles. We also have some underwater vehicles. We also have some ground robots. But we all come together and talk about UAVs. And the current projects we have are unmanned aerial systems for prescribed burns that I'm going to show you a video of, the water sampling that I'm going to show you a video of, and then at the end, if we have time, I have a video of the aerial vehicle that can land and dig a hole and fly away, which I like, and of a new swarm deployment system that we just developed. So first we'll start with prescribed fire that I think is really, really cool. So this is at Indian Cave. It's a really big park in Nebraska on the Missouri River, and we were told that we should burn these two areas. This is how they currently burn. There is a guy who walks around with a drip torch. It has diesel and gasoline inside, and he lights a fire line behind him as he walks, and then it blows away and starts fire everywhere else. And that's great on like really not slope surfaces that you can easily access. If you are looking at, oh, you can't see it very well. I'll hit the lights. If you're looking at the types of slopes here, it can get more dangerous. And so that's one of the things they wanted us to light. So usually they want you to light an area every 3 to 4 years, and it had been about 6 to 7 since they had burned this one. So it burned really nice. That was one fireball that burned that whole area. What you missed there was there are these ping pong balls. They have a dry material inside. We inject a wet material, and they ignite about 45 seconds later. So the mechanism to do that was created by Carrick Detweiler, one of the other co-directors of Nimbus. This is us surveying the area before we burned it. And in a second, you'll get to see all the smoke where we actually lit it on fire. So we got to fly over. We got to light it on fire. It worked really well. They were thrilled. It didn't, you can see there's still actually kind of a lot of leaves and stuff on the trees because it was more damp than they wanted it to be. But we were at the end of burning season, so they couldn't wait any longer. So their areas didn't burn very well either, just so you know. It wasn't just us. So that's the prescribed fire project. And then we also have an aerial water sampling project, and this is a lot brighter video, so I'm going to leave the video, or I'm going to leave the lights on. So the drone takes off. This is entirely autonomous. It goes over to the water. Now we're cheating a little bit because it goes to the middle of the area, so it's not right at the edges, which is actually on purpose. So things we assumed about water sampling before this was you could get water from anywhere, and it's basically the same. It's not. You don't need to do a lot of prep between getting water. You do, and getting water's easy. It's not. We lost 2 or 3 aircraft in water because, you know, aircraft and water don't mix very, very well. You can pull them back out, but if it's salt water, it's never going to fly again. And if it's been submerged for very long, it's never going to fly again. So things that we assumed but didn't know we were wrong about was cross-contamination between water areas. Depending on what they're looking for, can be really, really bad. So for this example, they were looking for invasive species. So if you take water from one pond to another pond, and you're testing for invasive species, you could be spreading that invasive species. So one of the things we had to work at was actually clearing the water line between samples. We're displacing graduate students. Sorry, everyone, I know. All the horrible things you have to do in your job, you all want the robots to do them. Well, the water sampling people actually got us to do that for them. Because grad students would either go out and they would have to collect right near the edge of the water, which is bad because if you're looking for like algae blooms and things, they kind of hang out right near the edge of the water, but the center could be fine. You can't take a boat into these different water areas for the same reason I just said, that if you take a boat from area to area, then you're spreading invasive species. And so we learned a lot about what water scientists do and the problems that they encounter in this project. And so for both of these projects, there is a user interface component that we have to work on. But there's also interacting with other people, right? So as this drone is going, if it can't get water from a specific area, maybe there's an algae bloom that's across the whole top, and there's nowhere good for it to actually get water. How do you convey these things? How do you tell them, hey, my mission is not going to be successful, or I know something you don't know, and get them to get the right information from you? And so that's really what motivates both the communication part And the distancing part really comes into play when you talk about other people being in the vicinity. So at prescribed burns, if you're going to drop fireballs, you probably want to maintain some amount of distance from people, but you're also going to need to probably take off and land where people are in the world. So how do you communicate about that? And how do you do it in such a way that you're not going to scare everyone to death? Very good. All right, so now we'll talk about distancing and communication in a more fundamental way. So to do this distancing work with small unmanned aerial systems, I actually looked at human-human studies. So how do people perceive each other, and how does that potentially generalize to ground robots, and then to unmanned aerial systems? So it turns out the human-human studies pretty well mapped exactly to ground robots, but they make a lot of the same assumptions, right? It's a ground-based entity with a somewhat similar footprint that will approach you in different ways. So what we did find from human-human and human-ground robot studies is the way that you approach someone is the same way that you expect them to approach you. And if they come closer than you would approach them, you'll back up. And if you go closer than they want you to come to them, they'll back up. That's how this works. You guys shift, and you kind of determine each other's comfortable space in this way. Now, really interesting things that you may never have thought about are that your personal space zone is actually more like a bubble. So it goes up above your head, and it gets compressed. So if you're in rooms with tall ceilings, you can be closer to people than if you're in rooms with short ceilings. It compresses the bubble and spreads out your space. And this happens for a couple of reasons. One of them is proxemics is based on a lot of sensing that you do with your body. So there is thermal sensing that you do. So if you're in a larger space, then the thermal energy dissipates easier. There's also auditory. So as you speak to other people, it's going to be louder in smaller space than it would be in a larger space, right, where it has more space to go away. And so there's all these things that change kind of what these zones are. They're fuzzy zones based on lots of things in the environment that impact it. So with that in mind, I replicated exactly a space from another study in 1982 that was on human-human approaches. So one thing that I did change, well, I changed two things. One is the robot and the subject are flipped. So the subject actually enters from the door, and the robot is on the other side of the room. So the robot's in here, and the subject enters over there. The reason I did that is because the robot needs to be in the room first so that we can make sure the room's calibrated and all those things. The robot's working. The other thing I did was I added a Vicon motion capture system to the room, which they didn't have in 1982 for them to get these really precise measurements of where everybody is in space and time throughout the study. The rest of it is pretty much the same. So the Vicon system actually will track, like I said, both entities so that we get these precise measurements. So what I did was I had a ground robot approach a person, a double telepresence robot. The double can be, if you haven't seen it, it has an adjustable height. So it can be from 1.19 meters to 1.52 meters. 1.52 meters is 5 feet, just so, because I can't do those kinds of maths in my head. So I'll tell you just so you know. The double weighs 6.8 kilograms, and then the aerial vehicle weighs about 400 grams. So the aerial vehicle we used was an Aztec Hummingbird. It's about this big, and it would take off and go towards the person at 5 feet, so they would be the same. So basically the experimental procedure that we used was inspired by human-human interactions, where the ground robot would approach the person, and when they felt uncomfortable, they would say stop. The robot would stop in a perfect world. Then the aerial vehicle would take off, go to a height of 5 feet, approach the person, and when they felt uncomfortable, they would say stop, and the robot would stop. And it really did stop. Sorry, I was just kidding. We didn't hit anybody in the face with a robot that I'm aware of. My grad students didn't cop to it if they did. But they both approached at 5 feet because that's one of the concerns. So when you're approaching somebody, one of the interesting things is that we have this kind of template matching that we do in our brain that goes back to our lizard brains, our evolutionary brains, where tall people, we have them stay further away from us than short people. And it turns out it's because they look the same size, right? So if you're tall, when you're further away from me, you look the same size as a short person when they're closer to me. And so that's why we kind of fix the height at 5 feet to see if that's true. Now, you can see where this breaks down with an aerial vehicle because We don't have a template for that. It's a buzzing thing that's flying at me. And so that's different. But we tried to fix as many things as we could. So the velocity of both were 0.2 meters per second. This was found in a human-human study to be the right approach speed, so that you are not too fast that people can't respond, but you're not too slow that they think you're a weirdo, I guess. And so it also allowed us to be safer when interacting with the participants. So if you're approaching this slowly, then they have plenty of time to tell you to stop, and you also have plenty of time to stop when they say to. Did you have a question? Yes.
Are they instructed to hold their ground and like not go closer or farther?
Yes. So we actually had them. Sorry, I'll flip back here. I don't know if you can see it very well. There's a little box right here that we asked them to stand in, and it had. It doesn't look like it does in the picture. In another study that I did, we actually had little feet marks for them to stand on. Like, these are your feet marks. One of the interesting things to me was that for the ground robot, a lot of them like looked at their feet and looked at the robot and looked at their feet and looked at the robot to see if it was going to hit their feet. So we could not coach them in every aspect of weird things that humans do. Like, if this robot's approaching you, you should look at it. So interesting things. But the results we found were basically that people were more comfortable with the double than they were with the aerial vehicle, which is great. We found this in two ways. One was that they increased their distance from the aerial vehicle compared to the double. The second one was that they actually had increased negative affect after interacting with the aerial vehicle compared to the double. And the concerning part to us was actually how close they let the UAV come, though. So a little over 2 feet is how close they let the UAV approach them, which is concerning because you can still stick your fingers in the blades, right? So 2 feet away is pretty close. It's also well within GPS error. So as we move this outside, the UAV can easily be pushed way too close. But the good thing is that you want the UAV more in your personal space zone than in your intimate zone. So the double they let approach within the intimate zone. There's a couple reasons we think that's true. One is it's so small and unimposing. Another one is it's designed to interact closely with you, right? That's what telepresence robots are supposed to do, is come and interact and talk to you and be your friend, but on an iPad. And so these are not entirely surprising results, and we'll talk more at the end of the talk about ways in which I'm hoping to make them more exciting. Other things I want to investigate that I think will be cooler. But it is a baseline for us to understand how people interact with them and what they think. All right, now we're going to shift tracks once I talk to them.
Have the face of a person on it?
No, it was actually a black screen. So this is a weakness. Good job seeing that. So the double had a black screen because we didn't want... So we talked about lots of different things we could put on the screen. Someone's face. So we could have the experimenter's face. Well, what if the experimenter's having a bad day and they're grumpier today? Okay, so what if we put a static face, just a picture of someone? Well, then are they focused on all of the wrong things about what they dislike about this person whose face you chose? Okay, well, let's put a fake face. We'll just put a smiley face. Well, no, because then this other thing. So we were trying to keep it with as few things that they could focus on as possible, but at the same time, it does create this void, right? Because a telepresence robot, by definition, should have someone's face on it. And so, yeah, it's one of those things where it was like a really difficult experimental design problem that we punted on because we just turned off the face. So, yes.
How loud is the hummingbird?
That's a great question. I have a video later that might have sound. If not, I'll play a video at the very end. So it's a little louder than an AR drone. It has AR drone props on it, but the motors are a little bit louder, a little bit whinier. So if you have that template, then you can expand from there. Yeah.
What about did you guys try anything at like lower altitudes? Because I know at like eye level, because I've worked with things at eye level, and it's like you're like, my eyes are pretty important, my feet not so much.
So yes, so that's a good point. Sorry, the 5 feet is right below eye level for our participant group. So our participant group was like 1.66 meters was the average eye height. We did measure that. We did not try other heights for this study. We did for a different study that I have not even written up the results for. It's not fully done, but from peeking at the results, people actually, there seems to be some sort of novelty effect that we're trying to get through and understand. But we did it at 3 feet, at 5 feet, and at 7 feet. And what we anticipated was people let the one at 7 feet come as close as we let it go, basically. That because it's above your head, no one's 7 feet tall. We haven't had any basketball players participate, so we were pretty safe in that. But no, it turned out people said the weirdest things, like, sorry, ladies. A lot of our female participants were like, but my hair. And I was like, but your eyes and like your body. But your hair, that's a bizarre thing for you to say to me, okay? And so your hair's also hopefully not like 2 feet above your body, if so we've got other problems going on. No, so we did try 3 feet, 5 feet, 7 feet. We actually got pretty much the same distance at all 3 altitudes, which was bizarre to us. But a lot of people, so what was interesting was in the interview, when we talked to them afterwards, a lot of people said in the 3-foot condition, oh, well, if it got too close and I got uncomfortable, I'd just kick it. And I was like, please don't kick my robot. But also, that's an interesting response. And so, because, you know, I thought 3 feet, for me, that's like all of my vital organs. So at 5 feet, I'm only 5'4". I can do this, right? That's easy. But at 3 feet, I'm kind of boxed into a corner, right? So I thought 3 feet would be scarier than 5 feet or 7 feet. But it turned out no. And at 5 feet, a couple of people did say something with their eyes, but we got a lot more of the I would kick it at 3 feet and butt my hair at 7 feet, which was bizarre to me. So we did get interesting interactions, as you always will when you interact with people. Anybody else? Yes?
Have your participant group largely interacted with drones before?
No. I'd have to go pull those numbers. Sorry. They're in the paper. No. So the participants we bring in, whenever I talk about bringing in novice participants, we actually, we do get some people from the computer science department, but we get almost no robotics students. So one of the interesting things about the Nimbus Lab is we have all of the robotics grad students in the department. So when we exclude our own students from studies, then we don't get robotics people. So we do ask very broad questions about how they interact with robots and how they have interacted with robots in the past. And so we actually give them examples like Robot Mindstorms, iRobot Roomba, to try to kind of shake loose, have you had robot interactions before? So we usually do get about half of our participants have interacted with a robot in some capacity. But like I said, they are not robotic students because we have the market cornered on that. There are mechanical engineering students who could come from across campus who students. They work primarily with medical robots. But for UAVs, it's a blessing and a curse that no. A lot of them do say, so usually about half will also say they have operated a UAV at some point in their life because so many people now have flown one of the little hobby ones or something. But a lot of them say like once. Great question. All right, communication through flight paths. So now we're going to switch tracks again and talk about flight paths. I'll motivate why I think flight paths are the right way to communicate first. Then I'll take you through 2 quick studies that we've done. One was presented at ICRA this year, and the other one is under preparation. So this was our cheesy NSF drawing for this project. This is our concept drawing for the prescribed burn. I know the video is much cooler than our concept drawing could ever hope to be. But basically, as these are becoming used in more public-facing applications, they need to be able to communicate with people who may or may not be operating them. So it is important to get your operator's attention if something's going wrong, but it's also important to be able to tell people who may not be involved in the operation that something has gone wrong and you need them to move out of the area, or you know something meaningful that they don't know, like I said. So one example is at the prescribed fire right here on the right, where you can imagine these 2 guys are controlling. They each have a robot they're controlling. This guy does not. If he was on the other side of the fire and one of those robots needed to land, or it saw, for instance, a fire outside the fire lines, it should communicate those things to him so that he can respond appropriately. So that's one of the states that they actually really want us to be able to communicate is if you see a fire outside the fire lines, that's real bad because you're trying to burn off fuel so that you don't have wildfires. And if there's a fire that could be starting, we want to put that out before it spreads. And so that is a common problem at these prescribed burns, and we'll talk more about that later. But other places that you could think about them needing to communicate with you are things like package delivery, photography. If somebody's out taking pictures or videos at a soccer game at a public park and something goes wrong with the vehicle, can it communicate that to people and get people out of the area before it lands? Things like that. That's that. So the first study that I did on this was super approachable because it was Amazon Mechanical Turk. So I'll go ahead and tell you up front, Mechanical Turk. But it was 64 users, and I basically took an initial set of gestures from avian gestures. So why do I love behavior-based gestures? I love them because there's an assumption that energy is important and should be conserved. They communicate in some meaningful way between species. So they communicate either within their own species or outside their species. And they are kind of robust to lighting conditions. They're usually easy to repeat. You can oscillate over them, things like that. So animal behaviors are really cool. So I went and found some bird behaviors. And I wanted to see if people had kind of inherent agreements upon what these different bird gestures could mean in the context of drones. So I created videos of these gestures, and I showed them to people. So it's 2 sets of 32 users. And in one case, 32 of these people got 2 labels to apply to a video. So they got either, so there's 7 labels: lost signal, change position, landing, missed goal, draw attention, lost sensor, and low battery. I picked those because they're labels that most drones should need at some point. People should have some context for. So things like lost signal and lost sensor and low battery you've seen on your phone, hopefully, or maybe hopefully not. But you have some context for those. You've also probably seen a drone in the air that has needed to land, or an airplane that has needed to land. And then you should understand things like change position or missed goal. So, and draw attention. So you've tried to do those things in your life. So these are things that people should be able to engage with. They should be pretty robust to any application you may need to convey these things, and people should have some context for them. So then I showed them either 2 of these label options or all 7, and I asked them to label the videos. So here's a video of a drone doing what looks like a Ferris wheel kind of maneuver. What do you think that means? Do you think it means it needs to attract attention? Do you think it's landing? Do you think it's doing something else? So the primary finding of this work was that these flight paths could be used to communicate information about the UAV and its understanding of the world to diverse participants. So the ones that were really loved, I'll show you a video in a few minutes, or on the next slide. That gives you a little bit more context. But spiral could be used to indicate landing in both conditions. So both under 2 labels and under 7 labels, more than half people assigned spiral to landing. And it's nice because it can also it can indicate both that is landing and where it's going. So I love that. Circle could be used to attract attention. So it had greater than 40% agreement in the 7 choice conditions. So it had a lot of agreement. And so we think those could be used kind of today. Now you may ask, because everyone always does, why not use lights and sounds? And so while the next video is getting started, it's going to tell you a lot of the things that I have already told you. And so I'll tell you why not lights and sounds. So there are lots of small unmanned aerial vehicles that are already out in the world. There are hobbyist systems. There are photography systems. Not all of them have lights. The ones that do probably don't have lights that you could repurpose to convey meaningful information. So this is circle. It was draw attention by participants. This is the figure 8. I thought it would be lost sensor because that's what you do for your magnetometer on your phone if it goes out. But people didn't remember that, I guess. So in the 2 choice condition, they did say lost sensor, but they actually thought it was change position otherwise. Left and right, I really thought looks like you're shaking your head. No. But nobody got that. So they didn't have a consensus on that one. Loop, this is the one I said looks like a Ferris wheel. People thought it was landing because it goes so close to the ground, I think. If it was high up in the air, maybe they wouldn't say that. Spiral, so this is what landing looks like to most people. And then swoop was labeled as draw attention, so it kind of swoops up and down. And undulate, it's kind of a sinusoidal wave, and they said this looked like draw attention. So thank goodness they didn't say low battery for that one. Up, down, we thought would look like you were nodding your head. It also had low agreement for participants. So now you'll be surprised, because in the next study, a lot of these motions are going to show back up. So people online couldn't label them the first time, but then when I asked people to design their own, a lot of these came back. So, all right, so the next study I did was called a guessability study. So it was a design-based approach adopted from HumanComputer Interaction, where I brought in people from the general public. So again, I just sent out, we post flyers, we send out emails, we get people from the general community, we advertise to local retirees who take classes on campus. So we try to get really diverse participants. And so you'll see that if you go look up any of the papers, you'll see generally a pretty broad spectrum of age ranges, which I love. I think that's really important. And so when I say general public, I do mean like not, 18 to 22-year-olds with a standard deviation of 2. So I do mean general public. So first, we had the participants come in, and we gave them a small drone model. It's like a third of the size of one of our drones. And we said, okay, so here's your drone, and you have this space to operate in. So we gave them kind of a cube of space to operate in. Please show us how it would convey these 7 states. So the same 7 states from the previous study. Low battery, attract attention, missed goal, those sorts of things. And so we said, write down on paper what you would do, and then show us what it would do, what its flight path would look like. And so they did that. They designed them on paper, then they showed them to the researcher, and then they said, I am either super confident or not confident at all that this will actually convey something to someone else in the world. The researcher then took these paths, went to our Vicon cage, programmed them in. We called it the drone copycat code, where you could just walk the drone around the cage and save that flight path. And so they didn't actually have to do any programming. They could just show the drone what to do. Then the participant came back and observed the flight path to give feedback to the people and say, hey, I thought it would be bigger, I thought it would be faster, I thought it would do this or that. So out of 140 gestures that they designed, only 4 of them we didn't get right the first time, and we corrected those pretty easily. Then they reported on their confidence that these would actually convey the information to people. All right, we designed a taxonomy. Yeah, I'll go through real fast. Sorry, I know we're getting close to the end of time. But basically, we adopted complexity, space, and cyclicity from other people's work. So other people who have created either drone flight paths or done guessability studies. And so we had these different, so simple versus compound gestures. So complexity is either it's one line or it's many lines. Space is it's either going directly from here to that trash can, or it's kind of taking a roundabout path from here to the trash can. Cyclicity is, does it actually cycle through multiple times, or is it just once? Command, so this is kind of fuzzed out from dimensionality, which is used in other works. So 2 dimensions versus 3 dimensions versus 4. It could be the axes that it works on. But for us, we actually boiled it down to roll, pitch, yaw, and throttle, because we thought that would be a better way to represent it for drones. Altitude, we included because every single participant mentioned something about the altitude. Either it goes up, it goes down, it stays the same, or it moves around in altitude. So they did key in that for UAVs, altitude is super important. And then motion, it's either kind of squarish, circle-ish, it rotates, or it does some combination of those. So we got good iterator reliability. I'll kind of fuzz over this because it's not super important for you guys, but hey, we got almost perfect on 4 of those categories, and 2 were substantial agreement. So our raters did kind of agree on things. Now, the interesting part to me is how we could classify those things and say that attract attention uses roll and throttle. So they're doing some sort of lateral motion, and they're going up and down for attract attention. Same for sensor loss. The rest of the things stayed the same. For low battery, they used multiple lines, and they used throttle. It was either decreasing or variable. So there's an example from low battery of something that somebody designed. So they had it come down, and then they had to go up and down when it was close to the ground to say, hey, I'm I'm doing something different. Signal loss was complex, so it had multiple lines, but everything else was pretty much the same. Area of interest and missed goal or target were curvilinear. They used roll and pitch, so there's an example from missed goal. Picture this on a plane this way, and so it's kind of a half circle in space. And then landing was direct, throttle, and decreasing, which means they actually wanted it to just land. So the common suggested flight paths that they came up with may look very familiar from the video that I showed you earlier. For landing and attract attention, they just wanted it to land. For area of interest, miss goal and target, and attract attention, they wanted to do a circle. For low battery and attract attention, they wanted to go up and down, which is bad for low battery. But that's what happens when you bring in novices. And then for sensor loss and signal loss, they just wanted to rotate in place. They wanted to yaw in place. And so the number in parentheses is the number of people who actually said that this is what they wanted to do. So 13 people for landing was just land. So we're looking at flight paths from prescribed burn community on these states, as well as ones such as embers expected or spot fire detected, like we talked about earlier. And next, we're going to extend to other platforms for the distancing. So we want to see if you have a small platform that's this big, do people let it come basically wherever they want, versus if you take a quad rotor and you make it bigger, do they not? We're going to add new states to communicate to gestures, and particularly look at how these gestures would impact a person, right? So that's one thing that we're not looking at right now is, what do you need to respond if it does this thing? So that may have a big impact on how they convey things to it. And eventually we want to merge the distancing and the gestures to appropriately size things to the environment that people are in. And you should care because they're going to be more prevalent in public spaces, so we want you to interact as safely as possible, maintain some sense of approach, space, and have comfortable approaches, and understand concerning states and community of flight paths. And I will end on this Nimbus Lab Facilities one, where you can see all of our cool drones. So all the way down here are the little bitty guys, and this one is almost 8 feet from prop tip to prop tip. So it's a big, heavy guy that's scary. It weighs about 40 pounds. So I will take your questions now. We have like 4 minutes. And if you don't have more questions, then I have more videos, but I'm just going to leave those out for right now. Yeah.
So you're basically using motion, which is like the modality for it to function, for also communication. Have you thought about adding other channels, like having LEDs on the system, maybe projections onto the floor, things like that, like channels specifically for communication?
Yep.
And especially I'm thinking for people who reuse the robot a lot, those like maybe it's not as intuitive first time,
right?
But still things like, you know, indicators which side you're going, things like that.
Yeah. So so there's been some really cool work on LEDs for communication. So Dan Zaffer's done like really cool stuff with having blinkers that tell you where you're going to go, or having eyes that show kind of where you're looking, different things like that. So what I'm trying to start with is stuff that every drone has, so that every drone can communicate. Basically, think of it as a package you could download to any drone system and have it actually communicate out in the world. But yes, I think those are important modalities to look at some point. The idea of projectors is cool. We actually, for fire, we're trying to figure out what we could augment it with that would make it easier. But the problem with fire is most people don't know how loud fires are. So you don't think about it, but you can hear the crackling in your fireplace. When it's large swaths of land that are on fire, it's super duper loud. And so that is something to overcome. But lights don't work well because there's smoke. So there's all these really cool challenges with fire. And so once you start kind of constraining yourself to an application area, that can kind of constrain your thinking on things like projectors and lights and sounds. So yes and no. But one of the things we are looking at, a question I get a lot is the drones are out there, they have a purpose. And so if you have them start communicating via flight path, it interferes with their purpose. So how do they prioritize these two competing objectives? And that's actually one of the things we're writing into hopefully our next proposal is how you can kind of have a time budget or an allocation of energy or something that would be how much energy can you expend on communication versus how much do you need to save for your actual mission objectives. With that, okay. So while we're talking, I'll just show you, because I like this video. This is a digging video. I have no control over the sound. There we go. I did get control over the sound. I'm sorry. My keyboard sound buttons don't work. So the drone comes in and lands. Come on, get to the cool part. Okay, so it lands, starts digging a hole, which is just really cool because they asked us to do this, and we were like, "There's no way," and then we figured out a way. And so it digs a hole, it leaves the sensor, and it will fly away, leaving the sensor behind that looks kind of like an ant mound in the ground. So. It's a DoD-sponsored project, so they're going to put whatever they want in the ground. But yeah, you can use it for crop planting. No, they're using it to sense different things in the environment. Then we did a swarm drop test, and that's kind of cool. So again, I'll just let this play. But I'm happy to answer questions while this plays. I just didn't want you to miss out on the cool videos, because that's what's here.
Users would design things that would characterize them as throttling or affecting the throttle. How much can you actually modulate the throttling to use that as a channel of communication besides just the throttle is increasing the throttle?
Yeah. So the command category looks at roll versus pitch versus yaw versus throttle. So it's just saying you can only modulate it up and down. But it's just saying they use that channel. So did they use that channel and this channel? So in which case they're doing some sort of, they could be doing this, but they're not doing, some kind of globy spiral thing. So it's just saying which ways are they interacting. And so I think those are important because you can design other gestures based on those same command profiles, particularly given that you know the altitude as well. So you know whether the altitude is increasing, decreasing, variable, or stable. So is it staying in one plane, or is it actually changing its height in some meaningful way?
How much can you change the actual sound that the propellers are making without destabilizing the drone or having another impact?
Very little. Very little. So you can do some changing of the sound in very small ways, but it depends on the system and it depends on a lot of other factors. So there were things that they wanted to do, like rock in place, that you really can't meaningfully do on a drone system, and so that we would change into kind of like a rock like this, and they were okay with that. They thought it conveyed the same thing.
Less in the motion side of things, but if you take, because I know microcontrollers are getting pretty darn fast now, and I think even a lot of store-bought ESCs, you can get like things on the nanosecond scale where it's actually able to get a nice resolution. I wonder if there's a way maybe to like leverage the yaw mechanics, like the propellers, and just spin up these two a little faster, a little slower,
Right.
to generate an actual audible noise, like
Right.
Even a voice.
Yeah.
Because if you can do it fast enough, then you're good to go.
I had not thought
So, this sort of on the same topic of like effective ways for the drone to communicate. I think the drone that I remember from the video was sort of like mid-size, which meant that it's sort of limited in how quickly it can move to indicate things. And also, I don't think it had like a visible eye, something that looks like eyes. So my thought was, if you have a very, very small drone that can move very quickly, and also it has something that looks like eyes or part of the face or something, even if it's just like a stereo camera, then I think a lot of normal gestures that people do with their head, like they tilt their head to indicate confusion, or like they nod or whatever, I think that would work. Just because it's so fast, I think it would work better.
No, I think that's true.
Yeah.
So all the other studies I did, so prior to getting to Nebraska, all of my robots had cameras on them. Once I got to Nebraska, not all the robots have cameras because that's not always their purpose. And so that's something that I honestly didn't think about the first study that we did with the distancing. The double has obvious cameras and obvious face, and the drone doesn't. It's just an X configuration. It doesn't have anything like that. And so I think that, again, gives people kind of a focal point. So the air robot that I used in grad school had a camera that hung below it, and it was like a very obvious, it was a canister. It looked like a camera, and so people kind of immediately were drawn to that. And so, yeah, I think that's true. I think that's something we could definitely look at. Thank you.
Let's thank the speaker again.